So we're going to leave semi-simple algebras alone for a little while. We've used them and their Cartan decomposition to sort of discover this geometric notion of a root system. So now we've got to just study root systems by themselves for a little while. So let me just remind you of the general notation. E is a Euclidean space. So a finite dimensional real vector space with an inner product. And a couple of other pieces of notation I always use when I write alpha check. That stands for 2 alpha over alpha alpha for any, well, it's going to be any root alpha, but any just non-zero element of E, that makes sense. And S alpha from E to E, that's the linear map, which is reflection in the hyperplane. Alpha perp. Alpha perp is the hyperplane orthogonal to alpha, right? So we're just in Euclidean space, so you have excellent geometric intuition. So remember the formula S alpha of some element lambda, it's just lambda minus lambda alpha check alpha. So that's kind of the first place you see this alpha check notation is convenient, is in that reflection formula. And then a root system, it's a subset R of Euclidean space so that R is finite and spans E. If you have alpha in R, a root, then a scalar multiple of alpha is in R if and only if C is plus or minus 1. That in particular means that stupidly, 0, it doesn't count as a root. That axiom gives you that none of these roots are 0, so this alpha check notation makes sense for any roots. Then axiom 3 was saying that if you take R and you apply any of these reflections, well, you get R back again. And axiom 4 is about these inner products beta alpha check. It says these are integers for all roots alpha and beta. Okay, so that's our axiom system. We've forgotten about the semi-simple Lie algebra that produced a root system for us at the end of the previous chapter, and we're just going to study these abstract root systems. So this is just a kind of a piece of elementary Euclidean geometry going on. One piece of notation, I'll often just use the word rank. The rank of a root system, that just means the dimension of the Euclidean space. Okay, so let's work out some basic properties. So we're just kind of starting with that list of axioms. What can we just prove from scratch? So the first lemma is that if you have alpha and beta being roots, with alpha not equal to plus or minus beta, so that means that alpha and beta are linearly independent due to our first axiom. Then look at the inner product, alpha beta. If it's positive, then alpha minus beta is a root. If it's negative, then alpha plus beta is a root. Okay, so we're doing just simple Euclidean geometry here. So I guess I should write down that the inner product alpha beta is the length of alpha, length of beta times the cosine of the angle in between them. So the two pictures in these two cases that you should have in mind are that maybe I'll actually draw a picture. There we go. You've got alpha somewhere, and you've got beta somewhere, and there's the angle between them. So it's either that the angle between them is acute, and in that case, the lemma is saying that alpha minus beta is a root, but alpha minus beta will be, let me see, so I've got to go to alpha and then minus beta. So yeah, that's sort of going to be this distance over here. So it's about there, isn't it, in the picture? somewhere there, there's alpha minus beta. That's going to be a root. That's the first case. And in the second case, this is when the angle between alpha and beta is obtuse, so beta somewhere over here. That's when that inner product alpha beta is negative. And then in that case, we're saying that, let me see, I've got to kind of go over here. This guy right here, this will be alpha plus beta. So this is the case when the angle is obtuse. Okay, so let's just prove the lemma in general. It's very straightforward, but it's kind of the beginning of seeing how rigid these axioms are. So let me just prove the first case. So I'm going to assume that alpha beta is positive. So let's see, let's look at beta alpha check. So by the definition, right, that's twice beta alpha over alpha alpha, and you just write that down, and some cancelling occurs. You end up with 2 beta over alpha cos theta. So if you take beta alpha check and you multiply by alpha beta check, well, some more cancelling occurs, and you get 4 cos squared theta. But this guy is an integer, and this guy is an integer, and this guy, it's, we're assuming that they're not at right angles to each other, because this inner product is not 0, so cos theta is not plus or minus 1, so this is definitely less than 4. So we're looking at an integer between 0 and 4, so it has to be just 1, 2, or 3. So there's very little possibility for these two integers. Their product is 1, 2, or 3. So one of them has to be 1, and the other one has to be 1, 2, or 3. Well, the thing we're proving symmetric in alpha and beta. So how about we assume without loss of generality that alpha beta check is 1, and then beta alpha check will be 1, 2, or 3. And then all you have to do is you have to then look at just S beta of alpha. So that's alpha minus alpha beta check beta. We're assuming that alpha beta check's 1 now, so this is just alpha minus beta. It's a root by axiom 3. So that proves the lemma, but you see the lemma actually kind of reveals this decisive fact, this property that these products, beta alpha beta check, are just 0, 1, 2, or 3 in general. I mean, they could be orthogonal. I wasn't considering that case in the lemma. So let's just make a little table. This is for alpha and beta in R, which are linearly independent. And we basically just used this in the lemma. Alpha beta check, beta alpha check. Let's put in theta, the angle between them, and let's put maybe the ratio of the length of beta over the length of alpha. That's useful to see that in the table as well. So I guess they could be orthogonal, totally possible. That's when the angle between them is pi by 2, and then that ratio could be pretty much anything. There's nothing that gives you any information about that. Or this guy could be 1, and the other guy could be 1, 2, or 3. Those were the cases we just saw when we were assuming that this angle was acute. So in these cases, the angle has to be pi by 3, pi by 4, or pi by 6. And this ratio of lengths, length of beta over length of alpha, it has to be 1, root 2, or root 3. That's the only way to solve this equation for this being 1, 2, or 3, given this formula for beta alpha check. Or I guess they could be negative. I was assuming it was positive, but the other cases are just very similar. So here the angle would be, so that this is the obtuse angle instead with the negative cosine. So this would be 2 pi by 3, 3 pi by 4, or 5 pi by 6, and the ratios of lengths, I guess it's going to go the It'll be the same ratios of lengths. So there we go. Or, of course, you can flip these two columns and then you have to take 1 over the last column. So up to switching alpha and beta, these are all of the possibilities. So that's, anyway, the first lemma and that useful table where you start seeing that there really aren't very many configurations, at least for a pair of linearly independent roots. Next lemma. So I'm going to continue looking at this situation. A pair of linearly independent roots. Now I'm going to let R and Q be maximal, so that beta minus R alpha and beta plus Q alpha are both roots. Then beta plus I alpha is a root for all I between minus R and Q. Moreover, this integer beta alpha check is equal to R minus Q. Of course, we already know from the table that this is 0 plus or minus 1 plus or minus 2 plus or minus 3. So actually, we've kind of seen this before. We saw this in, I think it was lemma 3 at the end of the last chapter. But there we were in the setting of a semi-simple Lie algebra, and we proved it by using representation theory of SL2. But so this was this thing, I called it the alpha string through beta. So here's the bottom of the alpha string through beta, and then you go through everything in between all the way up to beta plus Q alpha. So all our roots. When we proved it coming from a semi-simple Lie algebra in chapter 2, we looked at the little SL2, S alpha, associated to alpha, and all of these root spaces in our Lie algebra G were one-dimensional, and we found that this was actually an irreducible representation of that SL2. So this string was coming from that SL2 string of one irreducible representation. But of course, now we don't have a semi-simple Lie algebra around, so we've got to give a proof of this independent of what we did before, just using our axioms of root system. So let's do that. So I've got to prove that every beta plus I alpha in between is also a root. So let's suppose that some beta plus I alpha is not a root, and let's get a contradiction. So let me pick I minimal with I between minus R and Q. So beta plus I alpha is not a root. And let me pick J maximal between minus R and Q. So beta plus J alpha is not a root. Okay, so then what have we got? We've got, well, certainly I is going to be less than or equal to J. And we've got beta plus I alpha is not a root, but the one right before will be a root. And if we apply lemma 1 to this situation, we deduce that this inner product, beta plus I minus 1 alpha, alpha has to be greater than or equal to 0, because if it was negative, well, then lemma 1 would say that the sum of these two roots was a root, but we're assuming it's not. Do the same thing with J. Beta plus J alpha is not a root, but the next one up is a root because J was maximal. So now we can apply lemma 1 in just the same way to the inner product beta plus j plus 1 alpha alpha. That has to be less than or equal to 0, because if it was positive, then the difference between these two guys would be a root, but we're assuming it's not. Okay, and then I just subtract these two inequalities. So what have I got? I've got the betas cancel when I subtract. I've got I minus 1 alphas minus j minus 1 alphas. So that's I minus j minus 2 inner product of alpha with itself is greater than or equal to 0. But of course this is strictly positive. We're in a product space, and this, because I is less than or equal to j, that's negative, and that's a contradiction. Okay, so that's proved pretty much everything. I've just got to prove that equality there, that beta alpha check is R minus Q. And to do that, I'm just going to think about what this reflection S alpha does to one of these roots in this alpha string through beta. So by definition of reflection, it's beta plus I alpha, and then you have to take this inner product. So that's going to be beta minus beta alpha check alpha minus I alpha. Let's just check that. So I've got the beta alpha check alpha that I'm subtracting there. Here, the inner product of alpha with alpha check is 2 by the definition of alpha check. So I've got I alpha and I get minus 2 I alphas from here. So yeah, I've got minus I alpha overall. So what this is doing to the string as I gets bigger, when you reflect, you get this guy with with alphas being subtracted. So you get another guy in the string. And because this is just a reflection and this string is finite, this means that S alpha must actually just be giving a bijection from this string to this string. And it's just got to be just flipping it upside down, because plus I is going to minus I there. So this must just reverse the entire string. So in particular, when you plug in the guy at the top of the string, which is Q alpha, you must get the guy at the bottom of the string, which is beta minus R alpha. So this has got to be beta minus beta alpha check alpha minus Q alpha. So we deduce, what do we get? We get that R is beta alpha check plus Q. So yes, beta alpha check is R minus Q. So that's kind of an important formula. This R, it's how far beta is from the bottom of the string, and the Q is how far beta is from the top of the string. And these strings are not very long, because this difference R minus Q, it's just between minus 3 and 3. Anyway, that completes the proof of lemma 2. So let's now try and work out some examples. So the most trivial example is called the root system A1. It's of rank 1. And the only possibility when the Euclidean space is one-dimensional, well, there's the origin in my one-dimensional Euclidean space. You have to have a root alpha and then a root minus alpha. So the root system is just two guys plus or minus alpha. It's pretty boring, but there it is. That's the rank 1 root system. So let's go up to rank 2. So two-dimensional Euclidean space. So this is good because now I can genuinely draw them in the plane. The next example, it's a little bit boring, but we should start with it. It's called A1 cross A1. And it's just taking two copies of the A1 root system and I'm taking the direct sum of those vector spaces, the orthogonal direct sum of those vector spaces. So there's 4 roots, plus or minus alpha, plus or minus beta. Not very interesting because it's just 2 copies of A1 there sitting in disguise. Okay, that doesn't look like those are the same length, but there we go. Good enough. So now that corresponds to our table. That corresponds to this top row of our table when alpha and beta are at right angles. So then there are going to be 3 more, and I'm going to take alpha and beta to be obtuse when I'm drawing these pictures. So the 3 more correspond to these 3 remaining rows of this table. So the first one is when alpha and beta have the same length in that table. So this is called the root system A2. And so for this, I want to basically draw a regular hexagon. So how does that look? Roughly hexagonal. Let's see if it's not too bad. I think I need to just move this a little bit. I'm not very good at drawing. There we go. That looks more hexagonal now, doesn't it? So there we go. I've got vertices of a regular hexagon. There's the origin. So I want to take, you get these 6 roots around here. Let me call that one alpha and that one beta. And then this will be alpha plus beta. This is minus alpha minus beta minus alpha. So in this case, the size of the root system is 6. So what I've just done is I've just drawn this when alpha beta check is -1 and beta alpha check is -1. So in this case, the angle theta between these 2 guys is, let me see, it's 2 pi by 3, and the length of alpha is equal to the length of beta. Okay, so from that, you just draw your picture. That's how the configuration has to be for this root system in that case. So you take your alpha and your beta, and then you just close up under reflections, and this is what you end up with. So let me see, in this one we can already see the alpha string through beta. So right here, that's the alpha string through beta. It's got length 2. I guess we could have seen the alpha string through beta here as well. It's a bit boring. There's the alpha string through beta. It's got length 1. Okay, and so then there's these 2 more pictures corresponding to the final 2 cases in our table. The first of these cases is called B2, and then the other one is going to be G2. So the names are the same as the names of the Dinkin diagrams, which you've seen before. So for B2, well, B2 is kind of easy to draw. You just draw a square. And so this is the B2 root system. So then we join in the diagonals. Not too bad. There we go. So there's this. So right here is the root alpha. And then this is going to be the root beta. So here I'm drawing the situation where alpha beta check is -1 and beta alpha check is -2. The angle between them is 3 pi by 4, and the length of beta is root 2 times the length of alpha. Okay, so that's exactly what I've got here. So the other roots, when you just sort of close up under these reflections, the sort of smallest thing that you have to get so that the axioms are satisfied. So this would be beta plus alpha, beta plus 2 alpha, minus alpha, minus beta, minus 2 alpha, minus beta, minus alpha, and minus beta. So that's a picture of the B2 root system, and you can see right up here, There is the alpha string through beta, which now has length 3. And then the final one is this G2 root system when alpha beta check is going to be -1, beta alpha check is going to be -3, theta is going to be 5 pi by 6, and now the length of beta is going to be √3 times the length of alpha. Okay, so this one, to draw this one, you have to draw two equilateral triangles. That's not too bad. Then another one, and you stick that one on top, something like that. There we go. So this is going to be my G2 root system. So the origin somewhere in there. Okay, it's looking a little bit cluttered. There we go. This is the G2 root system. So this guy right here will be the, let's make maybe this guy here alpha, and I'm putting x's for my roots, aren't I? So that's going to be alpha, the short root, and this is going to be beta, the long root. And so there's the picture. Let me see, this is going to be beta plus alpha, beta plus 2 alpha, beta plus 3 alpha. Right here, this is going to be 2 beta plus 3 alpha, and then of course the negatives. I'm taking a little bit of time to draw these pictures because, well, you often need to look back at the rank 2 root systems when you're thinking about these things. And as we did before, let's just find the alpha string through beta. Well, that's going to be these guys right here. And now this has length 4. So these are actually all of the all of the rank 2 root systems. I guess we haven't proved that, but certainly we see that these are 4 rank 2 root systems: A1 cross A1, A2, B2, and G2. So I just took 2 linearly independent roots as in our table, and I just kind of closed up under reflections to build these things. Okay, so let's carry on talking about this sort of general setup of these root systems. So the next topic to discuss is bases. So here's the definition. A base for a root system is a subset delta of the roots such that delta is a basis for the vector space E, and if you have beta in R, which you can write as a linear combination C alpha alpha of the elements of your base, because it's a basis, either all C alpha are greater than or equal to 0, or all C alpha are less than or equal to 0. Okay, so that's the definition of a base. Given a base, I'll always just use alpha 1, alpha 2 up to alpha L for the elements of some base. So L here is then the rank of the root system, the dimension of the Euclidean space. We'll call the elements alpha I in delta the simple roots. Depends on the choice of base. And then any beta in in R in the root system is either a positive sum of alpha i's. That's the case when all these C alphas are positive, or it's a negative sum. That's this case. We'll call beta positive or negative accordingly. So our root system then decomposes into the disjoint union of positive roots and negative roots. All of this depends on being given a base. So once you've got a base, every root's either positive or negative. So the choice of a base gives you this decomposition of R into positive and negative roots. Maybe one other thing to note, that for alpha I and alpha J in the base, let me see, the inner product alpha I, alpha J, it has to be less than or equal to 0 by that first lemma. Because if this was positive, then alpha I minus alpha J would have been a root. But you see, all roots are either just positive linear combinations of the alphas or negative linear combinations. So some mixed guy like this with some positive and some negative coefficients can't possibly be a root. Okay, so the alpha i's in the base, they're all at obtuse angles to each other. Okay, so that's all given a base, right? So that was a bit of a stretch, given a base. So we need a theorem. Bases exist for any root system. And I decided I'm not going to write out the full details of the proof. I'm going to just refer you to the Humphreys book if you want to read the full details of the proof. I think it's in section 10.1. But I'm going to show you just the construction. Of bases and the full details of the proof that this indeed does produce a basis, a base of the root system, where you can look it up or work it out for yourself. It's not super hard. So the construction, the idea is you consider your Euclidean space and then you take away the union of all of those hyperplanes, all of those reflecting hyperplanes, alpha perp. So this has a bunch of connected components. Right, we've taken a Euclidean space, real vector space, and we've just thrown away a bunch of codimension 1 subspaces. So they cut this Euclidean space up into different connected components, which are called chambers. Right, so the connected components of E take away all these hyperplanes orthogonal to all of your roots, these hyperplanes that the S alphas are reflections in. Okay, so there's this notion of a chamber. Given a chamber, C, what you do is you define delta sub C, so given a connected component of this topological space, define delta sub C to be all roots alpha such that alpha perp is one of the bounding hyperplanes of C, and alpha is at an acute angle to every vector in the chamber C. Then the theorem, the proof of the theorem, which I'm skipping, shows that delta C is a base, and moreover, all bases arise from chambers in this way. Okay, so I'm sort of trying to just like move us forward just a little bit by not writing out all the details of that proof. It's not super hard, but I think it's better just to see this construction. So let's now go back to our examples and think, what are the chambers? What are the bases? I guess we should start with A1. So A1, there's just, so this is the reflecting hyperplane. So there's just this chamber and this chamber. Those are the two connected components when we throw away the origin. And so if you pick, maybe we pick this chamber here, call it C, and then delta C, so it's all alphas, so that the hyperplane orthogonal to alpha is a bounding hyperplane of the chamber. Well, that's both alphas. And then we want alpha to be at an acute angle to everything in the chamber. So actually, this guy here, these are the guys in the chamber. That's at an obtuse angle, right? So this is a degenerate case. In this case, delta sub C is just alpha. That's the base for this root system. And yes, this guy is plus alpha, and the only other root is minus alpha. That's a base. This one, so the alpha perp is that hyperplane, beta perp is that hyperplane. So our R2, our Euclidean space, has been cut up into 4 chambers. And if I pick one of the chambers, they all look basically the same, right? So if I pick this as my favorite chamber, that'll be the fundamental chamber, then which roots have I got that are, so alpha perp is a bounding hyperplane of C, beta perp is a bounding hyperplane of C, and the angle between alpha and anything in that chamber, the angle between beta and anything in that chamber is acute. So in this case, delta C for that chamber is just alpha and beta. These guys are no good because the angle between them and vectors in the chamber is obtuse. Okay, so there we go. That's the chamber. And so in this case, you see there's actually a choice of 4 different chambers. If you pick this chamber, you get alpha beta as the base, but I could have picked this chamber here, and then I'd have got alpha minus beta as a base, and so on. But picking alpha and beta, you can see everything's either alpha or beta. That's a positive sum of the alphas and betas, or negative sum of the alpha or betas. That's a base. Moving on, let's look at A2. So now I'm going to need a different color, I think. I'm going to mark the reflecting hyperplanes. So the hyperplane orthogonal to alpha, that's alpha perp. That's beta perp in there. And this is the final one. Okay, let me actually go straight through. There we go. That's good enough for our purposes, I think. So the blues are the reflecting hyperplanes. This is alpha perp. This is beta perp. And then the other one would be alpha plus beta perp, right in here. Okay, so those blue lines, you remove them, and you get this R2, this Euclidean space, cut up into 6 chambers. And if I pick one of the chambers, let me see which chamber do I want to pick. I'm going to pick this chamber right here. And if I call that C, then delta sub C, so the base corresponding to that choice of chamber. So I want all of the roots, so that so what are the bounding hyperplanes of that chamber? Alpha perp and beta perp. So the roots whose hyperplanes bound that chamber plus or minus alpha, plus or minus beta. But I don't pick minus alpha or minus beta because they're at obtuse angles to vectors in that chamber. I pick alpha, so I pick that beta because that's at an acute angle, and I pick that alpha because that's at an acute angle to everything in there. So the base is indeed just alpha and beta in this case. And you see all of the roots, they're either alpha, beta, or alpha plus beta. Those are the positive roots, or they're minus. These are going to be the negative roots coming from that base. Quickly going through B2 and G2. So I'm just going to shade my favorite chamber here. So that would be this one right here. This time the reflecting hyperplanes are just the lines I've drawn again. So if I were to take that as the chamber C, then delta C, it would be alpha and beta. So I'm kind of picking that fundamental chamber the way I've kind of labeled my roots, so that alpha beta is the base. In this case, if I want alpha and beta to be the base, I should pick, let me see, alpha, I should pick this guy right here as the chamber C, and then again delta C is alpha beta. Let's just check that. So again, in this picture, the reflecting hyperplanes are just these diagonals that I drew. This is alpha perp, this is beta perp. So yes, those hyperplanes are bounding hyperplanes for this choice of the chamber. And alpha is at an acute angle to everything inside, beta is at an acute angle to everything inside. And you'll find that none of the other roots satisfy all of those properties. So the base here is just this alpha beta. Okay, so this is sort of a nice way of picking a basis for the Euclidean space from the roots. I think we should stop there today, and I'll be talking about the Weil group next time.